Hello guys, today we are gonna analyze a combined cycle, and this combined cycle, as we recall, considers the joint of a gas cycle, gas power cycle, and a Rankine cycle. So let's start by reading this problem and then just highlight what is important in order to solve it. Well, we need to consider a combined gas steam power cycle. The topping cycle is a simple Brayton cycle that has a pressure ratio of 7. Air enters the compressor at 15 degrees at a rate of 40 kilograms per second, and the gas turbine at 950. The bottoming cycle is a reheat Rankine cycle between the pressure limits of 6 megapascal and 10 kilopascal. Steam is heated in a heat exchanger at a rate of 4.6 kilograms per second by exhaust gases leaving the gas turbine, and the exhaust gases leave the heat exchanger at 200 degrees Celsius. Steam leaves the high-pressure turbine at 1 megapascal and is reheated to 400 degrees in the heat exchanger before it expands in the low-pressure turbine. Assuming 80% efficiency for all pumps and turbines, determine the moisture content at the exit of the low-pressure turbine, the steam temperature at the inlet of the high-pressure turbine, and the net power output and the thermal efficiency of the combined plant. Okay, so let's first of all try to make sure that we have an understanding of where our data is. So we have a steam and gas power cycle. So let's differentiate. We are going to use this color for gas. So this is the gas cycle, and air is at 40 kilograms per second. So the mass flow rate of air is 40. On the other hand, this will be my steam cycle, and the mass flow rate of steam is 0.6. Okay, we have all the data for the Brayton cycle. We are giving the inlet temperature and the inlet pressure, so this state is known. We know the pressure ratio, so we can get H8, and since we have the isentropic efficiency, we can get the HAA. We're giving the inlet temperature, so we know state 9. Again, since we know the pressure ratio of 7 and the isentropic efficiency, we can get it state 10. And we are being told that the exhaust gases leave the heat exchanger at 200 degrees, so we have state 11. So all of the air cycle is defined. What about the steam cycle? Well, we know the low pressure, and the low pressure is 10 kilopascal. Since we know that condenses until it has a quality of 0, we know state 1. We know the state 2 is only the adding of the work of the pump, so this is known. We know the reheated temperature of 400 degrees and the pressure, so we know state 4. And since we know the isentropic efficiency, state 6 can be get. Now, if we check, one thing that we need is temperature 3. From temperature 3, we can derive state 4 and 6. Okay, so we are gonna proceed to solve. What we are gonna do is we're gonna start from the top. We are gonna solve, make the analysis, but we're not gonna get the numerical values. What we are gonna do is in the second video, we are gonna implement it in ease. Or you can go into the tables and get the correct answer. Okay, so let's start by going to our whiteboard. So just to make sure that we remember, what we need to find out is the quality at the exit of the turbine. We need to find out temperature 3, that's the temperature at the inlet of the steam turbine. We need to find out the network of the power plant, the net power, and the thermal efficiency. Okay, so let's start our analysis with the top level. And we're going to say that the thermal efficiency is the net power divided by the total heat that we are adding. Now we can start doing the first level analysis for each of the components as we have done in the past. So the Q in now for the work network we have two parts, the network so different colors for different fluids. Let's expand each of these. Again, doing first law analysis, we can get that the power of the turbine of air will be the mass flow rate of air times the enthalpy difference. And since we have the isentropic efficiency, we should consider actual conditions. Now, the work of the compressor, using first law, we have the mass flow rate times the enthalpy difference. And for the steam, okay, all of this is made with first law analysis. Now, how to get each of these states, each of these enthalpies, we need to consider each of the states. So we're going to find out. So let's start by the analysis to find out each of the properties. For the air, we are going to assume, and we can get it with this just to avoid the interpolation in tables F17. But if we decide to do with bar specific heats, we know how to use the tables. So for each H, we know that is CPT for each of the H that we need to find out, and CP is 1.005 kilojoules per kilograms, right? So we need to find each temperature. So for state 7, the entrance of the compressor, we have it. So that's done. In order to get T8S, we're going to use our isentropic expression. So from here we can get T8S. Now we need actual state, so we use isentropic efficiency of the compressor, and we know this value state 9 is also given. We're being told that is 950 degrees. So, and again, we can use isentropic relation to get T10S. So we can compute also using the definition of isentropic efficiency of the turbine. Finally, the state 11 is also given. And of course, let's remember that the isentropic efficiency of the compressor is equal to the isentropic efficiency of the turbine, and it's 80%. So we have complete the analysis for the air. We have all the data, and what we are going to move now is to have analysis of the steam cycle. So let's change colors here, and we're going to start by the data that we already know. So we said that we have state 1, and state 1 is given by two properties. Why do we need B1? Because to get state 2, 2s, you know that H2s is equal to H1 plus the mechanical energy that the pump is giving. And we know that P2 is equal to P3, right? Now, state 3, we know that 6 megapascal. State 3, we only know that pressure 3 is 6 megapascal, but we don't know that temperature 3 is actually one of the values that we need to get. Same with temperature 4, but we jump to temperature 5, state 5. After the reheat, we know the pressure. Why do we miss state 4? Let me just make it very clear. State 4, we know the pressure, and I will say pressure is 1 megapascal is the reheat pressure, and we know S3 equals S4, but we don't know this value since we only have one property here. And the property that we need to find out, put in a different color, is T3, which is an unknown at this point of time. Okay. Finally, so from here we can get state 6s. We know the pressure 6 is equal to pressure 1, which is 10 kilopascal. And S6 is equal to S5. From here we can get H5s. How are we going to get efficiency, the actual cycle? We get it from the definition of isentropic efficiency of the turbine. And here we get H6a. So the only two states that we're missing is state 3 and 4. So let's have a quick analysis on the heat exchanger, because that's where all of this is happening. So let's draw a diagram here, diagram of the heat exchanger. So I have my heat exchanger. Remember that this is a construction, a rigid construction, tube and shells usually, and we have 3 streams. The first stream comes from the air side. We have point 8A and leaves as point 11, right? And the mass flow rate that we have is the mass flow rate of air. And in counterflow, we have 2 streams of water. So for this heat exchanger, if we apply First law, and all the heat that we have, we want it from the air to the steam. We don't want any leak, right? That's something that we simply don't want. So the first law analysis for this system will yield to the summation of mass coming in times its enthalpy minus the summation of mass coming out times its enthalpy, and this will be equal to 0. Okay, if we expand this, and we're going to use different colors, so bear with me, we're going to have all the inlets first and all the outlets at the then. Okay. Okay, so we're going to call this the balance. And we can recognize that this is true only for one value. T3 is too high, you will have a different value, or if it's too high. So this balance will give you 0 only for a given value. The problem is that we have two unknowns. We have the temperature 3 and the state 4 that depends on state 3. So we are going to propose an iterative solution. And we are going to say that we start by guessing T3. Okay, so we guess T3. And this guess is just as initial point. It sure will not give us the right answer, but will help us to start the process going. As we know T3, then we can compute H3 and S3, because now this is given, right? Since it's given, we can compute H3 and S3. Now, since we know this, we can compute H4S. And since we compute H4S, we can compute now, right? So we know the two only values that we were missing in our equation was H4A and H3. We plug them here, so now we can compute the balance. I will say plug balance is this equation. If the answer is yes, then we know T3. And if we know T3, these values will change to S3. We're going to compute H4S, and then using the isentropic efficiency of the turbine, we're going to get H4A. If the answer is no, we need to update, return to the iteration. So now we need to compute again H3 and S3, compute H4, H4A, plug the values, and go again. How long are we gonna make this? Well, we're gonna make it until we have two consecutive values with certain the variation is that's what is will do. But what we're gonna do by hand, you can say, okay, I would like to bracket. There will be some values of t. Let me make this T3, and we're gonna have in this the balance, right? We say that we have only one value that will make the balance equal to 0. So there will be some values of T3 that will make the balance less than 0, and some other values of T3 make the balance greater than 0. Once that we have two identified, what we are going to do is an interpolation, and this will be our T3. This will be an interpolation. For that to happen, we need to have a point that is below, and a point that is above. So we are bracketing, okay, the solution. Okay, guys, see the next video for the implementation of this in ease. Thank you. And try to solve it using tables. Okay, guys. Thank you very much.